The paper explores the use of cloud computing for high-performance computing resources, focusing on the potential gains and losses of using containers for HPC applications. It discusses the software stack, the workflow to compile and run HPX applications within containers, and investigates performance differences. The study also reviews related work in the field, including Docker container performance, integration of MPI with Docker containers, and overheads of computation and communication on Linux containers. The software stack of OctoTiger, a C++ astrophysics application for simulating stellar mergers, is primarily based on HPX, an asynchronous many-task runtime system. HPX enables efficient management of data and execution dependencies within OctoTiger through its task graph, which is constructed using C++ futures and continuations. It also supports distributed capabilities, allowing for asynchronous method calls on HPX components across compute nodes, and provides tight integrations with CUDA, ROCm, and one API for integrating asynchronous GPU kernels and CPU, GPU data transfers into the task graph. In addition to HPX, OctoTiger relies on Kokkos, a framework for developing performance-portable compute kernels, and HPX-Kokkos, a compatibility layer between HPX and Kokkos. This setup allows for seamless integration of Kokkos kernels into the HPX task graph, enabling asynchronous continuations for post-processing or communicating results automatically once kernels are completed. All major compute kernels in OctoTiger have been ported to Kokkos, supporting explicit SIMD vectorization when necessary. OctoTiger also utilizes CP-Puddle, a utility library for task-based GPU programming suited for use with HPX. It provides allocators for GPU buffers and executors for work aggregation, which helps avoid GPU device starvation when dealing with numerous small GPU kernels. This makes CP-Puddle particularly suited for adaptive, tree-based codes like OctoTiger. Other dependencies include HDF5 and Silo for handling input, output, HWLOC and Jamalloc for efficiency, and Boost for its various utilities. Depending on the target machine, CUDA, ROCm, or one API must be installed. The set of dependencies often requires working with different versions depending on the machine's requirements and available modules. OctoTiger model stars as self-gravitating, inviscid fluids, requiring two coupled solvers, the fast multipole method for the gravitational field generated by the fluid, and finite volumes for the hydrodynamic solver. It uses an adaptive octree as its data structure, focusing resolution on the atmosphere between the two stars where mass transfer occurs. Each tree node in OctoTiger contains an entire 8x8x8 subgrid, which is configurable at compile time. OctoTiger is entirely built upon HPX, with each tree node being an HPX component. HPX was chosen due to its convenience in managing distributed tree traversals from a developer's standpoint. It allows for asynchronous method calls on HPX components across compute nodes, and provides functionalities such as HPX mutex for parallelism and concurrency, as per the C++20 API. The paper discusses the use of HPX with Spack and Singularity Containers for the OctoTiger project, focusing on improving the build and dependency management process. It begins by explaining how HPX's distributed task management capabilities allow for efficient handling of tree traversal in the code, enabling parallel work availability and avoiding resource starvation in large-scale runs. In terms of build and dependency management, the authors criticize their previous custom bash build scripts for being unwieldy and difficult to maintain across different machines and platforms. They introduce Spack as a package manager that allows for the installation of multiple versions and configurations of software, providing flexibility and reproducibility in the build process. The paper highlights the creation of a new OctoTiger Spack package, which is now available in their GitHub repository and integrated into their C pipeline for testing on various machines. The paper also explores the use of singularity containers, which do not require root access, making them suitable for HPC resources and the cloud. Spack provides experimental support for generating container files from its package recipes, which can be used with Docker and Singularity. This aspect will be tested in the work presented in the paper. Overall, The paper presents a comprehensive approach to optimizing the build and dependency management process for the Octo Tiger project, leveraging HPX, Spack, and Singularity to enhance performance, portability, and reproducibility. In this study, we explore the utilization of HPX with Spack and Singularity Containers for executing complex computational tasks on high-performance computing (HPC) clusters. Our primary focus is on deploying Octo Tiger, a computational fluid dynamics code, using these tools. The workflow involves generating a Docker file that contains the operating system and Spack instructions to compile Octo Tiger. This Docker file is then converted into a Singularity container, which can be executed without root access. We use the cluster's job scheduler to submit the job within the container. The process of generating a Singularity image from a Docker file presents several challenges. First, we encountered issues with compiling Octo Tiger before containerization, particularly when adding vendor-specific compilers like Cray Compiling Environment (CCE), or IBM's compiler for Power Architecture. Second, the Docker image needs to be generated on the host architecture, but we had no access to an A64FX machine with Docker to compile the image. We utilized Docker's buildx command with support for Linux ARM64 to generate an A64FX-based image, although cross-compilation for the A64FX-based image using Docker's buildx command was problematic. Instead, we built Octo Tiger without Kokkos support using CMake. We also investigated the performance differences introduced by Singularity images on HPC clusters. To do this, we compiled the same version of Octo Tiger and all its dependencies using Spack. We then compiled Octo Tiger without any container on the node, and within Docker. After that, we ran the rotating star example on the node directly and within the image. On Supercomputer Fugaku, we present single-node scaling results. For distributed runs, additional effort was required to add FuSiju MPI with TofuD. The statistics for the regular and Singularity runs on Supercomputer Fugaku are shown in Table 1. The results indicate that there is a slight overhead when running within a Singularity container, with a median time of 277.3 seconds compared to 215.2 seconds for the regular run. This overhead could be attributed to the additional layer of abstraction introduced by the Singularity container. However, the standard deviation of 6.2 seconds for the Singularity runs suggests that the overhead is relatively consistent. This research paper focuses on evaluating the overhead of containers when using HPX-Kokkos in high-performance computing environments. The authors discuss their journey, highlighting the challenges and benefits of containerization. They emphasize that while containers offer advantages in terms of reproducibility, portability, and running HPC applications, building within a container is not always easier. The paper presents performance comparisons between regular and Singularity runs on two supercomputers, Fugaku and Diehl. On Fugaku, regular runs were found to be faster, whereas on Diehl, there were no significant differences in CPU runs, but the Singularity runs were faster for CPU and GPU runs. However, distributed runs in the container crashed. The study also notes that the performance gains on Fugaku were outweighed by the benefits of reproducibility and documentation of the build process. For future work, the authors aim to interface the FuSiju MPI with the container for distributed runs and investigate the performance differences observed in GPU runs. They also plan to expand their study to larger GPU-based supercomputers such as NERSC's Perlmutter. The paper concludes that containers provide benefits for reproducibility, portability, and running HPC applications, although building within a container can be challenging. The performance on Fugaku favored running outside the container, but the gains in reproducibility and documentation of the build process likely outweigh these performance differences. The supplementary materials, including all scripts, are available on GitHub. The research paper explores the integration of HPX with Spack and Singularity containers for high-performance computing applications, particularly focusing on the simulation of stellar mergers. It discusses various aspects such as task-based parallel programming technologies, containerization, and the role of dredge-up in double white dwarf mergers. The paper begins by discussing the importance of task-based parallel programming technologies in high-performance computing. It highlights HPX, a C++ standard library for parallelism and concurrency, which is designed to scale up to thousands of nodes and millions of cores. The authors also mention Kokkos, a performance-portable many-core programming model, and its extensions for the exascale era. The paper then delves into the world of containerization, emphasizing Docker as a lightweight Linux container for consistent development and deployment. It discusses the performance overhead comparison between hypervisor and container-based virtualization, as well as the evaluation of Docker containers for scientific workloads in the cloud. In terms of stellar mergers, the authors discuss the role of dredge-up in double white dwarf mergers, which is crucial for understanding the mass transfer process in these systems. They also introduce Octo-Tiger, a new 3D hydrodynamic code for stellar mergers that uses HPX parallelization. Furthermore, the paper addresses the challenges of reproducibility in high-performance computing, citing a community survey on reproducibility practices. It emphasizes the need for a portable SIMD primitive using Kokkos for heterogeneous architectures and the use of task-based parallel programming technologies for high-performance computing. Finally, the paper concludes with a discussion on the use of Spack and Singularity Containers in HPC environments, detailing their scalability and portability in production biological simulations. It also touches upon the performance evaluation of Docker containers for HPC applications and the integration of HPX with Kokkos for enhancing performance and portability. Overall, the paper provides a comprehensive overview of the integration of HPX with Spack and Singularity containers for high-performance computing, with a focus on stellar merger simulations. It covers various aspects such as task-based parallel programming, containerization, and the importance of reproducibility in HPC environments.